What I'm going to talk about today is mostly about routing. So when we started preparing for this early in the week, I was going through my slides and I said, oh my goodness, I don't have enough material. I'll have to add some more. And then yesterday when I was going over this with John, we said, oh my goodness, we have way too much material. We're never going to finish all of this. So bear with us. We will talk about routing until we run out of time, and hopefully we'll be able to tell you a comprehensive story throughout it.
Willem has 1 slide per minute here, so we can't hold him up.
So what I do need to recognize is the folks that keep our RMHAM network running. So the slides show the names of all of the people that are our NetOps team. They basically spend many, many hours every week making sure that our network keeps on running. At this time, our network consists of 246 sites and 110 devices. So it is a big network that we need to keep running. What you see over here on the side is our NetLab that we will be using today to demonstrate a number of things. This is about 10% of our network. There's 32 devices on here that sort of show our main backbone going from Buckhorn and Horsetooth in the northern end of the state down to Fremont, and actually Cedarwood is a little further south on the south end. And the network actually extends much further east and west. We basically go to Grand Junction on the west. Burlington is the furthest east, right? Or is it Lyman? And then north we extend into Wyoming and south into New Mexico. So this is also a good time to remind you that RMHAM is a 501c3 corporation. We do spend an awful lot of money maintaining this network, paying for things like site leases, just replacing hardware that's been taken out by lightning, all of the things that just is wear and tear on a big network like this.
Pretty typically anywhere between $10,000 and $15,000 a year for maintenance.
So if you would like to contribute to RMHAM, the website is a great place to go. Wayne N0POH will be here a little later today. He's always a good person to contact if you want to donate money. And of course, our big fundraiser for the year is the Swap Fest that Desiree referred to. So we would love it if you were to participate in that particular event. So let's start talking about what we need to do in terms of routing. So what it all comes down to is the internet protocol. The reason why we use IP to run our network is that it is very robust and very flexible. So we use technologies such as VoIP to link analog repeaters together. Devices such as DMR radios, of course, are inherently IP aware and they can talk to each other. But the whole network is basically no different than the kind of IP network that a large ISP would have. And so in order for IP to work, you need to have 3 unique things. You must have an IP address, you must have a net mask, and you must have a default gateway. If you don't have those 3 things, you can't participate in an IP network. And the reason why you need a unique IP address is that's how the rest of the network is going to find you. You need to have a net mask because the net mask tells you the difference between devices that are local, that you can talk to directly, versus devices that are remote and that you have to talk through a gateway. And of course, the third thing that you need is what's the address of that gateway, right? How do you find the device that if you don't know what to do with that packet, where are you going to send it? So that goes out your default gateway. So what is shown on the slide is the compact notation that basically summarizes those 3 things. your IP address, your net mask, which is often written as just a slash and a number. So /24 means there are 24 bits in your net mask. And then the IP address of your default gateway, which is often written as just a comma after your IP address. And so for something like on a Linux box, in your net manager settings, for example, if you specify your IP address like that, it knows everything that it needs to know. Now, of course, there's other things that are nice to have. If you're not John Maxwell, who remembers IP addresses, the rest of us would like to have nice names for devices, right? So router.saddleback.rmham or something like that. So for that, we typically use DNS, the Domain Name Service. So for that, obviously what you need to do in your IP configuration is to tell it where to go and look up those addresses. But you can do routing without that, right? That's a nicety that makes humans able to interact with the devices. The other thing that's important is NTP, the Network Time Protocol. In that case, we want to make sure that all our devices agree on what time it is. All of those things are typically set in your IP configuration, but for the most part, you can do without it. So in order to understand what we're going to talk about today, it's important to define a number of terms. So the first thing is that for the most part, when we communicate, we'll use Ethernet at the local level. Now, of course, there are other options as well, but Ethernet is sort of doing most of the heavy lifting. And for Ethernet, there are two important terms, what we call hubs and switches. So as an example, here is just a device that will act as either a hub or a switch. This happens to be a switch. But it's essentially a dumb device, right? You send packets to it, it broadcasts those packets out the other ports, and if it's a switch, it uses the MAC address, the hardware address of that device, to learn what is on each port, so that the traffic that comes out of each of those ports are just the ones that are appropriate to that. Once we start talking more about interconnecting sites, the two important terms that we're going to use is bridging and routing. The difference between a bridge and a route is that a bridge essentially just passes all of the traffic in both directions without any configuration. Typically, if a packet comes in one side, it gets sent to all of the other devices or a particular device on that particular subnet, and the traffic just passes back and forth. A router, on the other hand, is going to make an intelligent decision of what to do with every packet. It's going to look at the contents of that packet, and then depending on what the contents is, it's going to send it to a particular device. And that's the main topic that we're going to talk about today, is how do you explain to the router what you want to do with those packets. And so that routing rules is what's we need to apply. So a number of common terminologies that we're going to use is when we talk about the port on the router or the switch, it's typically referred to as an interface. That is very often a physical port, but it could also be a virtual port, right? So for example, if you set up a virtual private network, a VPN, that shows up as a virtual interface on your device, and you can talk to it like you would to a port. The local area network, the network that we're directly connected to, we'll often refer to as the LAN, and then the things outside our network, we'll typically refer to as the WAN, or we'll use a term like the WAN port as the ones that I talk over. The VPN I already mentioned. The VPN is essentially a tunnel. So it's a virtual circuit between one device and the next. And basically you push values in the one side and it pops out the other side, just like if you had a physical wire which you would like to talk over. a very much overloaded term is the term bridge. So a bridge can also mean that it is a part of the router that is a local switch. So often when I talk about the bridge on the router, it really means that it's a device that actually has several local ports that provides a local LAN as part of that router. Depending on the specific router that you use, that may or may not be the case. So the first thing that I want to do is talk a little bit about bridging. So over here on the NetLab, all of the purple wires that we show in reality are microwave links. So each of these purple wires actually represents a microwave connection in the 5 gigahertz ham band that talks between two sites. So here's an example of such a device. This is called an LHG, light head grid, a device that is basically capable of talking a few miles. Down here, I have something that's called a QRT, again, something that's good for a few miles. This one will go a little further because it runs higher power. But basically, it's a microwave transmitter, very similar to your Wi-Fi, and it uses a protocol very similar to it. They're all part of the 802.11 series of protocols. But when we talk about long-distance shots, this works slightly different than your regular Wi-Fi in the sense that the window that it has in order to receive an acknowledgement of the fact that it sent out a packet needs to be wider. Some of our really long shots are of the order of 80 to 90 miles, and the round trip time gets up into the low millisecond range in that case, right? So your general Wi-Fi is not going to work with that because it's looking for a very short window for acknowledgements, and so it'll just keep on retransmitting that packet. So there are some variations on those protocols, but as far as our understanding of how the system works, you can just think of it as a Wi-Fi connection. The main difference being that they're typically a point-to-point connection. So there's one radio at each end, as opposed to having all of you here join the access point that's in this room. So what I'm going to do here is to now actually replace one of these microwave links here that's represented by just a physical wire by an actual microwave connection. And so what I need to do is explain what you're seeing over here. So in this case, I'm running a program called CPing. So this program is actually running on this little Raspberry Pi up here. And all it does is once a second, it sends out a packet to all of the devices on this network and say, hey, are you still there? And then displays the time in milliseconds that it took for that packet to come back. So you'll see that most of these colors are showing up as blue or green. The blues are single milliseconds. The greens are tens of milliseconds. It basically just measures how fast that response comes back. In this network, because everything is directly corrected, we're talking about signal millisecond round trip times. In the real world, our round trip times in our network is in the low tens of milliseconds. So typically, we can traverse the entire network from north to south in around 10 to 20 milliseconds, which is really good for radio communications or any kind of audio traffic. So you'll see that there's a few things here that are showing up in red. That's basically meaning those things aren't there yet, but it's because I'm going to now add those to the network. So the top here represents the link that I'm going to be replacing. So right now, this microwave link represented by that wire basically goes from 10.20.17.1 down to 10.20.17.2. All of the stuff in the middle doesn't exist. And so 17.1 and 17.2 can directly talk to each other over this wire. So if I actually unplug this wire, you'll see that suddenly it has lost connection to AC0KQ because I can now no longer talk from this device through the network over to that particular device. So what I'm going to do is to insert a link. So I'm going to take this purple wire here and plug it into the saddleback side of things. And I should have rolled this differently so that it's not a giant crow's nest. Oh, come on. And I'm going to connect it to this wire. Where's board one? So I'm still doing the same thing, except now I just have a really long wire and I'm electrically connecting it in the middle, right? And what you'll see is that it's able to communicate with the two ends of saddleback and AC0KQ now. So I'm now going to replace this with a regular switch, right? So this switch is just an Ethernet switch. So if I plug into it these two wires, you'll see the lights light up here and the connection comes back. And so what this device does without any switching is to just pass those packets back and forth. So what actually happens on our real network is what I'll show you next. So the purple side I'm going to plug into this microwave. The red side I am going to plug into this microwave. And if you look at the side here, you'll notice that all of those green lights are lit up. What that means is that this microwave device and this microwave device have been associated with each other. And so in this case, you'll see that now suddenly we see all kinds of blue here, right? So the way that these devices are set up is purely as a bridge. And that is how all of these individual links are actually set up. They're basically just passing all of the traffic from the port on the one side to the port on the other side, even though it actually goes over a microwave link.
It looks like a wire to the devices. It doesn't matter.
So you can actually add additional devices to that circuit. And one of the ones that I'll show you here is this particular switch. So this happens to be a pretty smart device. It actually will allow you to do things like VLANs and other Ethernet switch devices.
That's RouterOS 301.
Sure.
You don't have enough time.
But this is really just a switch, right? It's a device that has an IP address, but as far as what it does to the packets, it just passes them straight through the circuit. So if I were to take this connector and simply plug them into this device, you'll notice that the lights just come on. It automatically starts passing the traffic, but I don't have to do any configuration on this device, right? So the key thing in all of this discussion, it's just going to be long enough, is that now not only do we have a bridge between these two routers that will all just pass the traffic, but I can actually address each of those individual devices in the network between those two. And that's a really critical part of how we actually manage our network, because we can actually talk to the Ethernet dishes or the microwave dishes on both ends, you can go in there and say, I've got interference on this frequency, I need to move them to a different frequency, or I see lots of packet loss, what's my signal strength like, and things like that. However, the bottom line in all of this is that between every router, all of the devices in the middle simply acts just like a piece of wire, right? So whether we have 5 devices in the chain the way we do here, or just have a physical wire connected between them, they simply pass the packets between them. So how are we going to use that to actually set up the overall network? Well, at the end point, at each of those sites, we have a router. And how a router generally works is that it's got some switching fabric that can, at line speeds, in other words, at the rate at which packets arrive at that router, decide to which port does that packet need to go. Now, if you imagine that, some devices run with 10 gigabit ports, that is an awful lot of packets every second that you need to decide where that should go. So how that's typically implemented in a higher end router that will cost you in the thousands of dollars is that it actually has some FPGA style logic built into it that can examine that packet and decide where it's going to go in a microsecond or even less than that. However, if it gets a packet that doesn't match the patterns that are encoded in that switching fabric, it needs to basically bump it up to the routing engine and say, I don't know what to do with this. Where does this go, right? And so that when you get these out of the normal sequence packets, things slow way down, and you get the kind of speeds that you would typically get out of just a regular computer where you're basically running at CPU speeds. The other thing that's very important to notice in this particular diagram is that I show at the bottom the local bridge or short ports. So on all of these Mikrotik devices that we have here, you'll see that they have basically 5 ports or 10 ports or 24 or 48 ports, depending on how big a router it is. As part of this router, there is actually a switching chip that will basically make some of the ports act just like a local switch. In Mikrotik parlance, we typically refer to that as the bridge. However, that bridge is just another port on the device. And so this is going to be super critical when we start looking at some of the later labs and we try to distinguish between what can my laptop do that is connected to the bridge versus what can the router itself do. Because when I talk to the router itself, I'm actually talking to the box here labeled router engine. Whereas if I use my laptop that is physically plugged into that device, I'm actually talking to that local bridge or switch port. And those two things are different. In general, though, when we talk about the ports, depending on what kind of router you're dealing with, there will be a number of ports that you can receive traffic over or send traffic across. So if you look at the NetLab here, you'll see that in some of these cases, there's 4 or 5 purple wires that all go into this. So these all represent connections to adjacent sites. And what we need to do is to figure out, okay, what traffic goes over each of those ports. That's kind of what this whole class is about. So how do we do that? Well, one way of doing things is static routing. So in static routing, you basically write a rule that says, if the packet looks like this, it goes there. This is a good way of doing things if you have a small network. but it doesn't give you any redundancy, right? So if one of those links goes down and you want to be able to route the traffic some other way, how are you going to deal with that? Well,
Besides taking 2 days to retype all the routes in?
the way that you typically do that is through something that's called dynamic routing. So in the RMHAM network, what we use is a protocol called OSPF, Open Shortest Path First. And basically how that works is that each router basically talks to its neighbors and says, hey, who else can you guys talk to? And it learns from that, oh, well, the router here to my right can talk to this other network, and it's only 2 hops away, whereas the router on my left can also talk to that same site, but it's now 9 hops away. So open shortest path say, oh, well, I'm going to go the 2 hop route because it's the shortest path. But if that link fails, then it says, oh, well, I guess the 9 hop path is my best option, so I'm just going to go that way. And the network stays up by automatically reconfiguring it. So as a demonstration here, what I'm going to do on the NetLab is break the connection between Saddleback and Squaw. And what you'll see happens is as soon as I unplug that connection,
It's a very fast failover.
was that plugged in the first place? I was testing this before the class, and I may have not plugged it in properly. Let me fail a different one. Let's do Squaw to Devil's Head. If I unplug that, you'll see there we have some failures.
It's still broken.
It healed this one down here real fast. Which one can I not talk to right now? Squaw. Why can I not talk to Squaw? I think I may have, I probably have something else unplugged, and now I've lost both my connections to Squaw.
You have to fix it in 15 minutes before Observium alerts.
Yes. So, as you can actually see here, the fact that that showed green for a while, it was actually taking another path, and then it basically healed the path and fixed it another way. So the key thing with OSPF is that it learns from its neighbors, and when it's on an Ethernet connection like this, it can actually physically sense that that connection is down, and it will actually react to that very fast. In an actual microwave situation, you can't actually see the link drop. You have to sense that all of the packets have gone away, and then heal it
The
that
link
way.
doesn't drop. The port usually stays up.
Correct. We'll figure out here in a minute how that works. So OSPF works well for up to roughly about 1,000 routers, or depending on how fast your routers actually are, you can probably go bigger than that. So a lot of the internal networking in large organizations, something like Verizon, for example, would use OSPF within their internal network. But then the limitation is that every router in the network knows about every other router in the network and how to get to that. That works okay if you have a few thousand routes to deal with. But what if you have to deal with the internet, where there are just gazillions of routes everywhere? You're not going to know about every router in the world. For that, we use something called BGP. BGP stands for the Border Gateway Protocol, and it's the thing that basically runs the internet, right? So all of the big service providers have these million-dollar routers that basically knows about how to get traffic to everybody else in the world, and you use BGP to configure that. That's way beyond what we're going to cover here in this class, so I'll just mention it. But BGP takes a lot of configuration because you have to explicitly on every port say, these are all the routes that are going to go there. Also, BGP is very slow compared to OSPF, right? So in OSPF, even if you have, 1,000 routers in the network, it's typically on the order of a few seconds to resolve for all of the routers, for all of the routes. For BGP, if you have a lot of routes, it could actually take several minutes to actually resolve. Typical. So, it's not something that is practical for us in an internal network. There's also something else that's called equal cost multipath, ECMP, which is sort of a generic term for a number of protocols that deals with, hey, I actually have 4 links that goes from this site to that site. Instead of just using one of them, what if I can actually just spread my traffic over all of these routes and make use of all of the bandwidth that I have available to me? OSPF, open shortest path first, basically says, this is the way to go, and all the traffic goes there, right? It's a link state protocol. Things like the ECMP protocols will say, okay, these are all my options. I'll spread the traffic over all of those. I am not going to talk about BGP and ECMP today, but just know that these things are out there. So that brings us to the big question is, how does it know, right? How do you decide where to route to? Well, everything in terms of a routing decision is based on a subnet address, right? So subnets prior to 1993 were these things called class A, B, and C. And basically, depending on the first octet or maybe the first 2 octets, if you're the first octet is between 1 and 127, you are a class A address, and you deal with it in that way. If it's an address, let's say, between 128 and 200, then it's a class B. Class Cs are ones where the first 3 octets are important. Well, we thought that this was going to run the internet forever for about 2 years. So in 1993, a new concept that's called classless interdomain routing was introduced. And essentially what that says is, the individual numeric values of those octets no longer have any meaning. Instead, what we're going to do is we're going to take that address and we're going to break it into a network part and a host part, but we can break it anywhere within those 32 bits that are used by IPv4. And so whenever we talk about subnets today, completely forget about everything that existed, in the 80s and early 90s. Everything basically today works on CIDR.
What was the magic reason that they did it in 1993?
We ran out of addresses.
No, that's when the internet went public.
Well, that's true also. But that's when we ran out of addresses.
What? Al Gore did invent it.
That happened in 1993.
He's responsible for the Al Gore.
So the key thing about this idea of a subnet is that the devices that are within your subnet, you can talk to directly. But if you want to talk to a device that's on a different subnet, that's where routing comes in, right? You have to write the routing rules that is going to then decide how do you get to that. So this is what it looks like, right? So all of the IPv4 addresses is basically a 32-bit number. And what I've done here is to break up the different octets by doing a background color so you can count those bits easier. So we always count them from left to right because we're dealing with different kinds of hardware. In the networking world, everything is always stored big endian. So the most significant byte is on the left, the least significant byte is on the right. And I've also coded that depending on the subnet address. So you'll see that my address that I picked here was 10.11.128/28, right? So the first 28 bits on the left are all colored in blue. So that's all your subnet addresses. And then on the right-hand side is the host addresses, and those are shown in red. So in particular, in this case, my internet address encodes 10.11.12, and then the last octet is 128. So if you count these bits, you'll see that the first number is 10, the next number is 11, the next number is 12, and then in the last word, the 128 is split into the high 4 and the low 4. The high 4 representing 100 is the network part. The 000 is the network part. And so whenever we're talking about a subnet, there are always these specifically assigned values that have specific host quantities. If it's all zeros, that's your network address. The network address is not usable by a device as an address that it can talk to. It's a way of representing talking to the entire network. And the host bits there, those last 4 zeros, represents the address that's associated with the network. The net mask can be represented by either /28, or you can write it as 255, 255, 255.240. That basically means we've got all 1 bits in the blue fields and all zeros in the red fields, right? So that basically is a mask that we can apply to the individual IP addresses to tell what subnet it belongs to. The usable host addresses that we get out of this particular subnet are 10.11.12.129 through 10.11.12.142. And if you look at the bits here, you'll see that the lowest host address has basically got a 1 for the host field, whereas the highest has 1110, right? So it's 1 short of all 1s. Those are the usable addresses, and for a /28, there are 16 addresses. All zeros represents the network, 14 represent the hosts, and then we have 1 more, which we call the broadcast address. The broadcast address that has all 1s means that you're not talking to any individual device, you're talking to all of them, right? So we use the broadcast address, for example, to do things like address discovery, or you can send a ping to the broadcast address and basically say, hey, who's out there? And they will all reply back to that. But the key thing here is that in order to do routing, we need to be able to go from an IP address to a network address. So how do we do that? Well, what we do is we take one of these host addresses and we AND it with the net mask. The effect of the net mask is simply to knock down all of the bits that are the host address, and it gives you the network address. Once you know the network address, now you can make a decision as to what to actually do with that packet, right? So that's a really critical part of figuring out how routing works. So let's say we have the network address. We now want to decide where to send it. Well, let's say what I want to do is I have 3 ports, and the addresses that are, or the network routes that are associated with those 3 ports are 10.0.0.0/8. On gateway 1, I have 10.11.0.0.16. And on gateway 2, I have 10.11.12.0/24. Notice that those overlap.
Yes.
And in fact, there's one more address, which is what we call our default gateway address, which is 0.0.0.0/0. That matches everything.
Everybody.
So if I have a particular address, how do I define what the best match is. The most specific or the most bits in the network that will actually match. So it's not uncommon to actually have routes that looks like that actually overlap. What we do when we set routes is to, instead of saying, send over this gateway all packets that match this but not match that, instead what we do is we say, this is what I want to send over that address. And by making that very specific, having lots of bits that match, that's where the traffic goes, right? So the best match is always defined as the most network bits that actually match. So it's really important to get this. So I'll work through an example here. So I've got 5 gateways, 0 through 4. And these are the routes that are associated with each of those. So the first one, 000/0, is my default gateway. I always have to have a default gateway because all of my packets have to go somewhere. So if I don't know what else to do, that's where I'm going to send that packet. Then I have one that is 10.0.0.8. I have one that's 10.0.0.16. Then I've got 10.45.0016. So notice that both of those have 16s in them. The fact that this happens to be a 0 is just a particular subnet, right? It doesn't give it any higher priority. And then the last one is 10.30.20.0.24. So if I have a packet that comes in and the destination address is 10.30.20.7, where is it going to go? Well, does it match there?
Yes.
It does, but there's no, the length of that subnet is 0. Does it match here?
Yes.
It does. It has 8 bits. That's a better match. Does it match here?
Yes. 10.0.0.0? 16?
It's 10.0.
Uh-huh.
I'm matching 10.30.
Okay.
Doesn't match. So our best match is still this one here. What about 10.45?
No.
Well, now here it's much more obvious that that second 0 means it doesn't match. How about this one?
Perfect match.
24, right? That's our best match. So that's going to go that way, right? So you always have to think about it in testing all of these gateways and see what they go. Similarly, the 10.45.05, it's pretty obvious that that's going to go to 3. What about 10.30.10.5?
It would match on the second one.
It will match here, but it's not going to match on any of these other ones, right? So it will actually go sort of to that generic address. And the same thing is true for 10.0.2.1, right? So even though these two look very differently, they're all going to go there. What if I ping 8.8.8.8?
Wouldn't match gateway 2.
That's
No.
correct.
But why does 10.30.10?
There's a more specific one that, so it does match, but,
10.30.
so it's 10,
The one second from the bottom,
this one, 10.30.10.1?
that should be gateway 1. Not gateway 2.
You're correct.
He is correct.
You are correct, thank you. I actually did that on purpose.
You stare at these long enough, and it just goes.
So what about 8.8.8.8?
It doesn't match anything
It-
except for,
It only matches the default one, right? So this is how you have to think about all of this.
Should I put that over the mic?
Yes, please.
So what we discovered is if you look at the first example, where do these go? 10.30.20. It would match gateway 4, but we are already established that 10.20.30 would not match gateway 2. So when we get down to the third address at 10.30.10, because it is not a 1030.0 or a 10.0. It also would not match gateway 2, so we'd have to go back to gateway 1. So that third example is
Correct.
incorrect.
Right.
The professor is schooled.
No, it was a test to see if you're paying attention. I've been doing this long enough to know how to cover up my mistakes. So another important thing to remember is what an IP packet actually looks like. So this shows the header of all IPv4 traffic. Actually, we'll also cover IPv6 because, well, actually not here with these, but so this version number here, those first 4 bytes, actually says this is IPv4, so it'll actually examine it. And IPv4 packets have 20 bytes or 20 bytes long. There's a bunch of interesting things in here, but the really important ones are this field here, the time to live, and these 2 fields here, the source address and the destination address. So both the source and destination address are each 32 bits long, and then the time to live is an 8-bit field. So that time to live is a way of preventing packets from just going around forever, right? So at some point, they will time out. So let's say we want to pass a packet from this device up here through all of these devices here, and then finally end up at one of these. What in that header gets changed as it goes from one router to the next? The only thing that changes is the time to live, right? Because that particular field basically counts how many hops has it gone. So as you go from one hop to the next, it decrements that field by 1. And when that field reaches 0, it basically says, it's never going to get there. So it'll send back a reply that says destination
exceeded.
unreachable.
TTL exceeded, destination unreachable.
Right. So when you try to make a TCP connection or you try to do a ping, you'll get that kind of error message. The key thing in all of this, though, is that that source and destination address never changes. So the question is, I started on this device, and I wanted to reach this one over here. How the heck did I get an IP packet from here to there? The source address will be the address of this device. The destination address will be the destination of this device. It's going to pass through this one here, but how is this one going to decide what to do?
It has a source and destination address. It knows how to get to the destination. It knows where it came from.
But so how do I get from here to here? It needs to go through this device. But how do I get it to this device? Don't I have to have a name by which to call this device in order to get the packet from here to there?
You only have to go to the next hop in the journey.
How do I do that?
Default gateway.
I do it with Ethernet,
Yes.
right? So your IP address or that IP packet is sent as the actual payload within an Ethernet frame, right? A frame and a packet is the same thing. We just call them different because we want to seem smart. In that particular Ethernet frame, there's a bunch of bits at the front that it just twiddles to say, hey, I want the line. And then there's a destination MAC address and a source MAC address, right? That's the physical device that is sending it and the physical device that this is addressed to. So when I want to send a packet from, let's say, Saddleback to Squaw over this wire, the IP packets only has the destination and the source for the ends of that connection. What we need to do in this particular router is to have a program with sufficient privileges that it will wrap that particular IP packet into an Ethernet frame, and I can choose on that router what the Ethernet address is of the next device that I need to send it to. That next device will say, hey, I recognize this packet is for me because it has my MAC address, but I see that the source and destination addresses of the IP packet that I encapsulated is not for me. What am I going to do? Well, I'm going to make a routing decision because I now act as a router. And in the Linux kernel, there's actually a bit that you need to set that enables routing, right? And it's called IPv4_forward. If that is not set, it'll basically say, I'm not the source, I'm not the destination, I don't care. I don't know why you sent this to me, it's not mine, right? However, if that forward bit is set, it will then go and look at its routing table, or if you're in a router, it'll basically look that up in the switching network and say, okay, now I need to send it to the next guy. Why is this such a big deal? It's a big deal because in order to get a packet from here to there, I need to be able to talk at layer 2. I need to be able to directly send a packet to a MAC address that I know. How do I know its MAC address? It's on my local subnet or a local subnet that I'm connected to, right? And that's the most critical thing to understand about routing, that in order to be able to send a packet to an attached router, you have to have a shared subnet, right? That shared subnet will then be able to encapsulate the packet to where it needs to go and basically send it to the next device that says, you deal with it, it's not here, right? And it will basically then, through the entire network, pass it from one device to the next, to the next, to the next. Basically, how that decision is made is that the router looks at the destination IP address. Does it care about the source address? Not if it's in the forward chain. The guy at the end needs to know where to send the answer back to, but all of the ones that forward only look at the destination IP address, and it then looks at its routing table at all of the routes that it has, and it takes that address and basically applies an AND between that IP address and the specific net mask for this particular route. So it's basically knocking off all of the host bits and then says, do I know what to do with this, right? And as we talked about when we were matching the rules, the default gateway is the place where it goes if we have no other fallback. Otherwise, we're going to find the one that's the best match, and that's where we're going to send it. So here's an example of what that would look like in practice, right? So SQA, this site right here, basically has a connection that goes to Saddleback, and it has a connection that goes to Devil's Head, right? It has two Ethernet ports, what I call Ether 1 and Ether 2 here, that basically sets the subnets that connected to those other devices. It also has a bridge. So the third port is actually all of the locally attached ports that we have. And then what we've done here is to set up a set of rules that say what traffic goes where, right? So the destination or the default gateway we can set to either end, right? There's no local Ethernet connection at SQA, or there wasn't at the time that I wrote the slide. So I have no way out. The only way that I can connect out is to either one of those two gateways, and I can set a set of rules. Notice that these rules actually overlap to some extent, right? So I have the destination address of 10.0.0.0.8 going to Saddleback, right? That's most of my traffic are going to go there. But if I want to talk to Devil's Head, which is 103050 or to Badger, that's 103060, I wanted to go out that way. Or if I want to talk to El Magre, I want to go out that way. So instead of saying, send this traffic to El Magre, but not that traffic, what I simply do is I write a generic rule that says, this is where most of my traffic goes, except for these, right? So these exceptions then say, oh, in those special cases, then I want it to go out that particular route, right? And that's the way that you have to think when you actually set up these individual ones. So basically, how you would then configure this is that you would, for each of the ports on the device, give it an IP address. So for the bridge, my IP address is typically the .1. That's the convention we follow. It's not required by the IP protocol, but that's a common one that we use. So that's 10.30.31. Ether 1 and Ether 2 would be 10.20.13.1 or 10.25.1. Is that? Yeah, that's actually correct. Notice that the convention that RMHAM follows is that the sites have a 30 for the second octet, and the links have a 20 for the second octet. That's for us that are not John Maxwell, that have to have some mnemonic that lets us figure out what the heck we're doing, right?
That is my mnemonic.
So the key thing to remember about this, and this is going to be very important when we do the next lab, is let's say I send a packet to 10.30.20.1, right? So that's Thoradin's address. When Squaw sends a packet to Thoradin, what does it say is its source address? If I'm logged into that router and it says I'm going to send out a packet across this interface, it doesn't use the address of the bridge, right? Remember, if we go back to the slide that showed this,
It's the link address.
when I am actually talking to the routing engine of the router, I'm over here. I'm not down here at the bridge. So if I now want to send a packet from here out a particular port, what is the source address of that port? Well, let's say I'm sending it over port 1.
It
It's
depends.
actually the address of port 1, right?
In the case of Squaw, it's 10.20.13.1.
So this is really important because when I now take my laptop and I plug it into the router, I'm actually not connecting to the router, I'm connecting to the bridge.
Which is 10.30.30 something.
So when I send a packet from the router will identify as a different source address than if I'm sending it from my laptop.
Depending on which way you go.
Agreed.
If
right?
you go to Saddleback from Squaw, it's 10.20.13. If you go to Devil's Head from Squaw, it's 10.25. So it depends on which way you go out of the site as to what it's going to be.
So why this is so important is that when we're going to test our routing, we're going to use two things. We're going to use ping, which just connects end to end, and we're going to use traceroute, which basically then tries to test all of the intermediate hops. You will very often find that, well, I can ping from the router, but I cannot ping from my laptop. Why? Right? That problem is one that's very often at the root of our routing mishaps, right? So you're beating your head against the wall because your laptop can't talk to all of the remote devices, but the router can, right? So you think there's something wrong with your routes out there. Well, it's actually to have something to do with how we've configured it. So we'll cover that in the next lab. So as I've mentioned, traceroute is a common way of actually testing our routes. What traceroute basically does is it constructs special packets where the time to live is 1 or 2 or 3 or 4. That's intentional, right? Normally when you send a packet, the time to live is 30, or if you're Google, 128. It basically says how many hops will you tolerate before you get to where you are. What traceroutes particularly does is it says, I'm going to send one with just one time to live to cause that device to time out and send me back a reply that says, hey, I'm Pete, your packet timed out, right? So I know now my first hop is Pete. Then the second one is, hey, this is Johnny. Okay, that's where the second one timed out. So you can actually track the route. Again, an important thing to remember is if you're a real geek and you run Linux, those packets that are sent by traceroute are UDP packets. If you're running on Windows, those are ICMP packets, right? Those are different protocols, and depending on how your firewalls are set up, some of those may behave differently. So just be aware that sometimes funky things happen. So I'm going to go 5 more minutes and then we'll take our break. So what often goes wrong with routing? Well, most often it's something like you forgot to put in a default route, right? You didn't have the ultimate fallback in there, or your default route goes the wrong way. So that's always the first thing to check. The more important one is I have a route to get from A to B, but I don't have a route to go from B back to A. How do we solve that? Well, we'll talk about that in a minute. The third problem is split routes. So you're sending out a packet through this port, and the reply comes back over that port, right? Some protocols will not work with that. And it sometimes has to do with how there's address translation that happens in the middle, and the source address is somehow different when it comes out of that port than when you send it out this way. And just correct.
You're having trouble Starlink, which you packets don't like to come back.
Well, and sometimes, you know, the routing, you have 2 routes that are equally weighted, and it just randomly picks one to send through, and you get a reply through another. That often doesn't make a difference, but in some protocols, it may. So we'll deal with that at the time. What drives us nuts are flapping VPNs. So what flapping VPNs very often result from is that you have an address that you need to talk to. To set up the VPN, you then set up the VPN, which brings up new routes, and suddenly one of those routes that you've just brought up is how you reach the other endpoint of the VPN. So the VPN is like a snake eating itself, right? It says, oh, I can actually reach the VPN by connecting over the VPN. Well, that results in a VPN that basically goes up and down and up and down and up and down, right? We call that flapping. Not going to have time to talk about that today, but if you have a VPN that keeps on going up and down and up and up and up and down, that's probably what you messed up. The key thing about routing is that there isn't a mistake that I haven't made more than 3 times in one day. So the long and the short of it is there are lots of really original or creative ways to mess things up. Those you only figure out through experience. So let's take our break now so we can recover my voice. I'll talk about NAT, and then we'll do our next lab. So I have 9:37, be back at 9:45. So let's talk about our next topic before we can actually do the next lab, which is network address translation. So Shortly after we thought that we had solved the world's problems by using CIDR, we once again ran out of IP addresses, because at last count, there were 27,645,432 devices on the internet. Don't fact check me on that. So the problem basically is in our IPv4 address space, we can only have 4 billion addresses, right? And as Bill Gates said, that should be enough for everybody, right? But clearly, we have at each of our homes probably dozens of devices that all need to talk to the internet. Well, there just isn't enough addresses to do that. So the solution that is very commonly used is called network address translation. So all of the devices on your local network has as its gateway your local router, right? Your router that you use to access the internet. And that device is set up to do NAT. The technical terms are either source NAT or masquerade. They mean almost the same thing, although there's a few technical differences. But what it comes down to is that when I send a packet from my laptop through that router to, let's say, Google, what the router does is it takes that IP packet, and unlike what I described in the routing definition here, it actually changes the source address to its own address. And so it then masquerades or pretends to be my device to the rest of the world, and when that packet then gets returned, it says, oh, this came back to me, but it actually originated at Willem's laptop, so I'm going to now rewrite the destination address to be Willem's laptop and send it back. So lots of devices will actually masquerade as your external address or your WAN address. If you're using a protocol like TCP or UDP, it's easy for the router to keep track of those connections by simply saying, oh, that IP address and that port, I'm going to remap to this IP address and port, and I'm going to use that to keep track of the connections. For other protocols like ICMP, that doesn't work because ICMP doesn't have a port. So it actually has to write the contents of that ICMP packet with a special flag that it can recognize when that packet comes back so that it can forward it. But that's just a technical detail. The way to think about NAT is that your device rewrites the source address to be itself as opposed to the device that actually originated it. That's great for outbound, but what if you actually need to connect to a device that's behind that particular router? That's referred to as destination NAT, or also called port forwarding. So what you basically say in that case is that when a connection arrives at the router for, let's say, port 80, HTTP, or your web connection, my web server is over there. I'm going to rewrite the destination address to be, or send it to that device, and then rewrite the source port so that that device will send that packet back to me. And then when I receive that, I will then rewrite the destination port to actually send it back to the device that it originally came from. So for our purposes here, we'll just mostly deal with outbound, but basically know that in the router, there are smarts that will actually change those IP addresses to make things work. So what could possibly go wrong? Sorry.
A lot of things can go wrong. So can you use source and destination at the same time in the same interface?
Yes, we do that all the time. The only problem occurs if you're not very specific about how you do it. So you can actually set the NATing to only occur depending on what the interface is that it's coming in from or going out across. And if you do that wrong, like I did at Cheyenne Mountain last week, basically the packet goes to the router and it says, oh, well, you must be sending it back to where it just came from, and it goes right back. So
Sometimes you want that. It's called hairpin NAT, but
sometimes that's desirable. It wasn't last week.
but just to repeat the question for those online, the question was, can you use source and destination NATing at the same time on the same interface? Answer is yes.
Yes, you have to qualify it on the interface, though. So where things go wrong with split routes is that in order for NATing to work, the packet needs to transition the same router because only that router knows about those, right? So if you send a packet out one router and a reply comes back in another, that other router doesn't know that the NAT needs to take place, right? So that's obviously going to be a problem.
They get lost and confused very easily.
Like me. But in most applications, you'll have one gateway address and it won't be a problem. The other thing that could go along with NAT, of course, is that the router actually needs to keep some state, right? It needs to remember what those connections are. So if either the router gets rebooted or something goes wrong, then all of that state is lost and you have to reestablish that connection. The other thing could also be, depending on what protocol you're using, there could just be no packet that go in one direction or the other for a very long period of time. And the router may say, well, you just didn't shut down this connection properly. I'm just going to forget about it, right? So that's often solved with something that's called a keep alive. A packet that just gets sent that says, hi, I'm still here. I don't have anything to say right now, but I'm still here, right? So that just keeps those connections correct. So let's actually try to add a new device to the NetLab. So what I've done here is I've taken a little Mikrotik router, ports 1 and 2. I have the Broncos colored.
Pointed at Mark.
Excuse me?
Pointed at Mark.
Oh, sorry. Ports 1 and 2 are the Bronco ports, right? The orange and blue ports. And I'm going to use those to connect to the NetLab. And then ports 3 to 4 is where I am physically connected to this device. So port 1 is the orange port. And I am going to take this orange wire. I think I'm going to take this orange wire.
We have too many wires. When they say this stuff is wireless, that's a misnomer.
I am going to plug this into buckhorn of my router. And what I'm next going to do is to launch Winbox. So you'll all remember Winbox from RouterOS 101, assuming that you did the homework assignment. And what Winbox allows me to do is to connect to this router, which I have configured here to have, a local address of 10.30.8.1, right? That's an address that's not in use.
That says 80.
What did I say?
8.
Sorry, brain fart. So there's my Winbox. And what I can do under the interfaces is see there's my 3 LAN ports, and then I have 2 WAN ports. So you'll see one of the WAN ports is actually up and running, right? That's the orange one that I've plugged in, and it recognized that there's something on the other end of that wire. But I don't have anything configured yet. So if I look at my address list, the only address that's associated with this router is on the bridge. And that bridge has on it my 3 LAN ports, right? So when I'm plugged into the LAN port, I'm talking to the bridge. I'm on the one side of the router. I now need to set up something on the WAN side of the router to actually connect to it. Well, that's actually a very simple process. So what I'm going to do is actually say what I want to do is simply set up a DHCP client, right? I'm going to ask the device on the remote side, hey, give me an IP address. So I'll add a DHCP client on Ether WAN 1 and say, if you know about DNS and you know about NTP, just go ahead and set those as well. Notice also it says add default route. What that will do is as soon as I make that connection, I am bound to it. And if I now look at my address list, I have the new address that I just got from that particular router. It happens to be 10.16.2.80. Well, I actually did an IP reservation so that it will give me address 80 so I can remember what that is for the rest of the lab. But that now actually set things up. And if I now start going here to tools, ping, I can ping 10.30.20.1. Or I hope I can. Magic. How did this router know how to get to Thornton? It had nowhere else to go with 10.30.20.1, so it says, send it on the orange wire. It sent that to Buckhorn. Buckhorn knew the rest of the world. Wonderful. So now everything is just going to work. So I can, on my laptop here, say, I want to ping 10.30.20.1. Crap. Okay, Emmett. What is wrong? Well, first question to ask is, where the hell are you coming from, right? I'm on my laptop.
I can answer that question.
On my laptop, I have a bunch of other crap, but 10.30.80.249 is my local address. Why can I not ping from 10.30.80.249 to Thornton, but I can from 10.30.80.1?
Because the rest of the world doesn't know how to get back to you.
No, because I am not coming from 10.30.80.1. Remember when we talked about sending pings out of over an interface? It's using the WAN address as the source address when it sends that packet. What is that WAN address?
10.16 something. 10.16.
It's 10.16.2.80. 10.16.2.80 is an address within the Buckhorn subnet. Everything knows how to get back to Buckhorn. I am part of Buckhorn, but nobody knows how to get to 10.30.80. Nobody knows about that. So how do I fix this problem?
There's two ways to do it.
There's the easy way and there's the hard way. What is the easy way?
No, that's static route and OSPF are one of the fixes, and that's the hard way. The other way is
I'm
where
going to
he's
go
going.
to IP firewall. Firewall, are you out of your mind? Well, what happens in Linux is there's a packet. So, of course, all of those routers actually run Linux under the hood, right? In Linux, there is something called netfilter. Netfilter is this very complicated arrangement that will look at the source and destination addresses and decide what to do, including changing them, right? So all of the things like NAT and forwarding and all of those actually happen in this one package. And so in RouterOS, they've actually put all of the forwarding, things like NAT, also in the firewall interface, right? because they're Linux geeks. They think like Linux, right? They don't think like regular Unix. So what I'm going to do here is just to say what I'm going to add is source net on the out interface WAN1 action masquerade. That sounds a little odd, but basically masquerade is NAT, network address translation. Now I can ping Thornton. I don't know. It always works.
No. The caveat to using network address translation is you cannot go from an inside address to an outside address and then expect to come back to the same address. You cannot do that.
Right. So the key thing here is that this orange wire contains addresses that are, that router is pretending to be itself, right? So when a packet goes from my laptop through that router and it ends up on this wire, it looks like Buckhorn. It doesn't look like I am connected to this router here. So NAT is a quick way of establishing a connection to the outbound world without having to deal with the complications of, well, I need to teach the rest of the outside world about me. But as John indicated, what if somebody needs to connect to my laptop?
You can do two things. There's always two things.
Well, first of all, do I want the rest of the world to connect to my laptop?
Not necessarily.
Probably not, right? So NAT is actually a fairly good safety mechanism, right? The reason why we NAT our home networks is generally that we can get out, but the outside world can only reach our gateway, right? It actually can't get to the inside of the network, and therefore they can't reach our devices, right? Unless we set up something like port forwarding, right? Where we specifically say, if you connect to my router, I will allow you to connect internally to my network.
With the port forward.
Using a port forward, right? And what we'll do in Lab 3 is we'll actually make ourselves part of the whole network, and we'll share equal access to the whole network. The problem is if you do that, you basically have to make sure that you have defense in depth, right? Not only do you firewall at where you connect to the world, but you better have firewalls on all of your local devices to keep things out.
So the caveat here is we do this internally, but our network is isolated from the rest of the world. We don't necessarily worry about the bad actors and the script kiddies in China or Russia getting into our stuff because everything that's inside the network is hidden from the outside of the network. Your mileage may vary in your case. If you have world routable addresses and you put them inside your network, that's where you got to worry about firewalls. Absolutely. And if you put them on spacecraft, that would be stupid.
Well, I mean, one of the things that we worry a lot about is, our microwave networks sometimes shoot over the top of other people. We don't want everybody to get into the internals of our network. So there are some ways that we can keep them out. So we've established that we can talk to the rest of the world, but let's say we want to move to something slightly more sophisticated. How are we going to do that? So you are just asking for it.
We got a message in the chat. Nate wants you to count in IPv6.
I don't understand the question. I refuse to understand the question.
Okay.
So let's say we set up our network where we connect to the outside world. So I've got an Ether WAN that is on 128.138. That happens to be CU Boulder's address space. So I'm on 32.18, that's my ISP. And I've set up a VPN to Thoradin on 172.16.20.7/24. So both of those are interfaces that I can now direct traffic across. And then for my bridge, I've chosen 129.168.27.1. 129.168 is basically private address space. So
Your dyslexia is kicking in. That's 192, not 129.
brain farts. That's why I have you here. To fix my
Okay.
mistakes. Let's think about how we would actually set up routes for those. So what am I going to use as my default gateway? Right? My default gateway is basically when I want to go to Facebook or Google or everything else, I want to send packets that way, right? So what is my default gateway? Well, it would probably be my ISP, right? Whoever I'm buying my internet service
Their
from,
router.
right? And in this case, my ISP, the University of Colorado, has told me that 128.138.32.1 is where their next clever router is. So I will set that as the default gateway. What I now want to do is to say, well, I have a VPN that goes up to Thoradin. So I actually have something very similar to what I have here. But instead of having that orange wire that goes up to Buckhorn, I have this virtual circuit that goes from my router to the RMHAM site at Thoradin. And I've set that up so that Thoradin is 172.16.20.1. That's shared by everything. And my local address is 172.16.20.77, right? So that's my local address that is at OVPN Thoradin. So typically how we would name those interfaces is by the protocol and where it's going. So in this case, I'm using the OVPN, OpenVPN protocol, and I'm connecting to Thoradin, right? Just again, so that I can remember what I'm doing. So what I now want to do is I want all of the traffic to the RMHAM network to go to Thoradin. So what is the RMHAM network? Well, it's anything that starts with 10 or 192.168 or 172.16. So what I want to do is be specific about sending that traffic to that particular interface. So in this case, I would set up static routes here so that 10.0.0.8 goes to 172.16.21, and 192.168.00.16 goes to 172.16.20.1, right? So that basically says anything that I want to talk about in the RMHAM network, I'm going to send over that OVPN pipe. However, when I now actually go and connect to my router, I'll see that there's actually a total of 6 routes that shows up. So one will show up as the default route, right? So 000. There'll be the 2 static routes that I've set, but there's also going to be 3 other routes that show up. Those are called directly attached, or also known as connected networks. What are those connected networks? Well, the network that I share with my ISP is 128.138.32.0. Why do I share a network with my ISP? I can't talk to the gateway unless we share a network, right? So that directly attached network or shared network is what I need to talk to my ISP. I also share a network with Thoradin, right? It's that virtual network that goes over the OVPN connection. And then I also have my local network, 192.168.27.0, which is basically my bridge network. So let's say I send a packet to the printer on my locally attached network that happens to have an IP address 192.168.27.108. What's going to happen to that packet?
Stays on the bridge.
But I just added a static route that says it should send those packets to authoritative.
It always goes to the smallest routing, the most specific route.
It always goes to the most specific route, right? So the reason that these are there is that in the routing table, it needs to explicitly know about what is local, right? And so that bridge actually has an address or a route that says, oh, you can just reach that directly, send that packet there instead of here, right? So if I wanted to make this more complicated and I wanted to send some traffic here, some traffic there, that's typically how we set things up, right? You always start with a default gateway. Where does it go if you know nothing else? And then get more and more specific, right? RMHAM traffic should go here, right? The local traffic should go there and so forth. So in terms of setting things up, that's typically how we do it.
Winbox in the IP routes command is really good at telling you which ones are directly attached. At the beginning of the line in IP routes, it will say DAC. That's directly attached, active, connected.
Correct. So this slide just repeats what I just said because this is really super important, right? You first set your default gateway. That default gateway, if it's not there, your VPN can't work, right? Because your VPN actually needs to connect out to another site in order to send that traffic there. So default gateway first, and then add more specific things as you go in there. If you're a true nerd, what you would do is you would log into the system using SSH, and at the command line, you would type IP, route add, destination address, whatever, gateway equals whatever, right? Or you can use the interface and basically set that. So in this case, what I've got is an orange wire that runs directly from here to Buckhorn. And if I were to snip that line, the electrical connections on both sides will know that those connections is severed and you can no longer communicate over it. What about a VPN? So in a VPN, I am connecting over some complicated network to something on the other side. Or in this case, I've got a microwave link that goes from the saddleback router to this microwave dish to this microwave dish through that Ethernet switch, sorry, right on there, back into there. What if this microwave dish went down? I pulled the power on it. Well, actually, I should do that one over there. Would the saddleback, with the AC0KQ side of the link, know that that microwave is down?
No,
Why not?
because the connection is still active.
Because
Not
I've got
passing
a
packets.
wire that goes from here all the way to there, and this wire says, hey, there's another device on the other side. That link's good. Why the heck aren't the packets showing up? Well, the other thing that you can add to that line, and I ran out of space doing it, is check gateway equals ping, right?
There's a pull down for that.
And what that will do is it will do an end-to-end test across the microwave that says, I can't talk to the device at the far side. I don't know why that is, but the device is no longer there. If the device is no longer there, that interface is not running, and I can't route packets across that. Right. Which brings me to the next point, right? I just invested in another ISP connection. So what I now want to do is use both the orange and the blue, and I want to now connect my router not only to Buckhorn, but I also want to go to Lee Hill.
Remember, the orange and the blue could be microwaves.
So here's the concept. I have two ISPs. If the one ISP goes down, I want to use the other one. Well, what do I have to do? Well, what I need to do is to set up failover, right? Failover is a simple way of adding redundancy without adding a lot of complexity. And basically what failover says is use this, but if that's broke, use that. How do I do that?
It's not OSPF, but OSPF would become a part of it.
So the slides here, I basically did it the nerd way, right? I have add gateway distance 1, add gateway distance 2. I didn't tell it what the destination is. If I don't tell it what the destination is, what's the destination?
Default.
The default route. Well, let's do it the lazy way. What I'm going to do here is get rid of all of the gazillions of screens that I have. I'm going to say IP DHCP client, add another DHCP client, but now go to WAN 2. Cool. Lee Hill just gave me a connection. Will any traffic go to it?
No.
Well, let's take a look at, Tristan is actually correct, right? We can't know yet. We
Yeah,
need to look at IP routes.
I just know what it's going to do.
And notice that route 1 is blue, route 2, 10.1 is black.
Notice that one of them has an A and one of them doesn't. The A is the one that's active. The dark one is the
You're
one that's
hiding
active.
behind the screen.
Yes, because I can't. I can't see it. I have old eyes.
Right? So it just, as Tristan pointed out, it's non-deterministic, right? We don't know what it's going to do. However, we actually have control over that. If I go to my interfaces here, I can tell it under the advanced options that the default route distance to Lee Hill should be 2. And I think I need to drop it before it'll actually take, oh no, it actually took
No,
right
I
away.
think it'll take it.
Right? So notice that I now have a distance 1 to Buckhorn and a distance 2 to Lee Hill. It's the same route, so the routing doesn't have a choice between one or the other in terms of the number of bits that match. They're equally specific, but by adding that distance, I said, I want to go to Buckhorn by preference, and I'll go to Lee Hill by second preference.
But it's still not going to work.
What did I leave out? Class? I need a natural, right? I need to apply the same natural to that particular device as I did for the first. So IP firewall. This sort of addresses Tristan's previous question. I'm going to do 2 source nets, I should say, but in this case, I specify a different interface to make that more specific. And then the action will be masquerade. So is this going to work?
Yes. No.
I made it specific to begin with, right? So I
you want me
said
to
WAN
unplug
1
it?
and WAN 2.
Start your ping.
Are you brave enough to let me test this? because if I screwed it up, I don't want to be embarrassed. So there started it. Hang on a second, let me get the screen up here.
All right, currently we're routing on the orange wire.
So, sorry, there's my route list. Okay, pull the orange wire.
Yeah, it's pretty fast. When you pull a physical interface, it knows immediately.
Plug it back in.
There's,
I was watching the thing in the back end, and it just kind of like.
which one? Bottom one?
Last one.
I forgot which one I
4.5.
pulled it out of.
Oh, that would be a problem. It should recognize, oh, there it is.
There it is.
It took a second before the WAN came up. Right? And so now it failed back to that, right? So failover is really easy to do, right? It's basically, as long as you have two choices, you go here. If you can't go there, you go the other one, right? Now notice that this is different than, for example, bonding, right? So bonding is one of those equal weight multiple path options, right? I have two connections. I should be using both of them, right? This doesn't address that. It's not going to send packets both ways. It's going to use one, and if that one goes down, it fails over to the second one, right? So what we typically do in this case is you pay a lot of money to your primary ISP, and you get an El Cheapo one for the second ISP. And if the primary goes down, you still have connectivity, but it's typically slower. Okay, so great. But oh, so there's the lab we just did.
Now we
What if the
really-
ISP goes down?
If the gateway is still up and the
So-
ISP can't route.
I can talk to my ISP, but my ISP had a fiber cut and he can no longer talk to the rest of the world.
How do you tell that?
I can't talk to the rest of the world. So I'm not,
No, waiting doesn't do it.
so the problem is everything here, I can ping my ISP. My ISP is just not routing my packets.
This is multiple hops down the road. You can tell if your first hop dies, that's very easy. It's past the first hop that this is going to work with.
So I am not actually going to do a demo of it, but if you really want to know, I have a resource at the end of the slide deck that shows you step by step how to do that.
I use this, and we use this on many of our gateways. When we lose a hop in the ISP, it's probably not at our site, it's probably somewhere down the road, but it will automatically fail over and then fail back when that route comes back up.
Yes.
That's what this
So
is.
what you do is you choose a reliable target. And that target, you have to be willing to sacrifice if your primary ISP goes down, right? So let's say in this case, I use Cloudflare 1.1.1.1, or you can use Google 8.8.8.8. Just don't then also use it for DNS, because if your primary ISP goes down, you can't talk to Google anymore, or at least not to 8.8.8.
You need a secondary DNS that's not going out that route.
And so the magic that I'm not going to go into the details of in the interest of time is that you set up a specific route to that one device, 1.1.1/32. Now, I chose that because that one device is actually not one device, it's all a Cloudflare, right? So there's a lot of redundancy built in there. And I say, across this particular interface, which happens to be Mountain Broadband, which is my interface, set up that route with a scope of 10. Now, I'm not going to go into the scope and target scope, but it's basically another level of selecting within the Mikrotik router as to what route is the one that I'm going to use. Then I say, okay, my default destination, the default gateway, happens to be gateway 1111. Now, that is not actually the gateway that it's going to send to. It's going to say, because my target scope is 11, the gateway that you should use is actually that gateway that I've specified there. How it's going to know whether that gateway is up is I'm going to send a packet through that particular interface, and if I get a reply from Cloudflare, all of my other traffic is going to go over that same route. If my ISP has a cable cut or a failure of some kind, that I can still talk to my ISP, but my ISP can talk to anything else, that address will no longer be reachable. And that will mask this default gateway as unreachable. Once that happens, well, what are your other choices, right? I've got some other ISP or other gateway that I would go to. But what this allows you to do is to, using the entire transport mechanism to this reliable host as the way of making sure that I have connectivity to the outside world. Now, what if Cloudflare goes down?
Anything out that route is down.
I don't know whether it's Cloudflare that's down or it's Google, that's my endpoint. Whatever your endpoint is, it's down, right? So pick something that's reliable, that is, if it goes down, it's probably the end of the world. So, you know, it can't just be, you know, your mom's house's IP address that's on Comcast that's down 3 times a day, right? It needs to be a reliable target. But this way, you can actually detect a much more complicated path, right? There's a lot more to this. Go read the notes. It's an assignment for the reader.
Extremely powerful and works very well. But it's cryptic, so pay attention.
So let's move on to the reason why you're here, OSPF, right? So what I'll do is I'll do a quick introduction to OSPF. We'll take another break, and then we'll do the lab. So what is OSPF? Well, it stands for Open Shortest Path First. It's actually officially defined as RFC 2328, and it's known as an interior gateway protocol. So you own the entire network. It's your routers. You control them. I am just going to set up routing between them. Right? If you have somebody outside your network that you need to talk to, you would typically resort to something like BGP. It's a link state routing protocol. So a link is either active or it's inactive. It's a binary choice. However, you can set a weight on every link and basically steer traffic by setting the cumulative weight along a path to something that is reasonable, right? So a common problem that we have is we have our microwave network, and for each of these links, we have a weight of 10, right? So to go from Lee Hill to Fremont, it's 1, 2, 3, 4, 5, 6 hops. The cost will be 60. However, actually it's Fremont's a poor choice. Let's use El Magre, so 5 hops. There's also this red wire that goes over to there and goes from that red box over to Lee Hill. That's only 2 hops. How do I tell it that, hey, that's a commercial ISP, right? Well, no, it's Mountain Broadband. They're actually really great. It's Skybeam at El Magre.
Rise.
Or Rise, whatever the heck they're called these days. Well, it used to be. The long and the short of it is that is a possible path, but it's an undesirable path, right? Because once you go via the commercial internet, it's probably going via Chicago, right? So your ping time may be 100 milliseconds. And for audio connections, that's terrible. So how do I tell OSPF, don't take the 2-hop route, take the 6-hop route? Thank you. Well, for the microwave links, we set all of those weights to 10, right? So the 6 translates to, yes. It's an arbitrary number. It's just a weight that we make up. What we typically do for the VPNs is to give it a weight like 5,000, right? You can have weights up to 64,000. So that 5,000 says the cost to go over the red wires via the ISP is now 5,000 to the red box, another 5,000 down to Almagre, so that total cost is 10,000. That's
long as it's
way more.
As long as it's more than the physical route over the microwave.
Right. And so what it's going to say is, well, both of those routes are open, they're both connected, but I'm going to send traffic down the cheapest path, right? And it's the sum of all of those links. And so typically what you want to be very careful for is if you have, let's say, in this case, I've added demo, I've plugged it into Buckhorn and I've plugged it into Lee Hill. When I turn on OSPF on this device, I want to make sure that OSPF doesn't suddenly think, oh, that's a really cool way to send all of the traffic. Let's set that all to the demo router and then send it from the demo router to Lee Hill, right? So those things will always put really big weights on something in the 1,000 or greater route to actually send it. So how does it actually work? Well, every router talks to their adjacent routers. They've got a special protocol, and it basically exchanges three important pieces of information. What static routes are local to that particular device? So I have a path that says this is how you get there. I'm going to let other people know. Then the directly attached routes, just the physical things that you're plugged in, but then it also shares what it has learned from all of its other routers. So for example, SQA through this purple wire here learns about all of these routers up here. How Saddleback learns about those routes is it learns it from the adjacent router, from SQA. And it figures then out what's the best way to get there using what's called Dijkstra's algorithm, right? Dijkstra is this computer scientist that has invented half of computer science and came up with this particular algorithm to find the shortest path giving this distributed rules. So the three laws of OSPF that you will remember and follow upon pain of death.
We found
First
out the hard
rule
way.
is never use static routes to point to another device that runs OSPF, right? So if you put in a static route, you are telling OSPF to get to that address, send stuff to me, I will get it there. That is probably the wrong answer for 99% of the rest of the routers on the network, right? So if the thing that you are pointing to runs OSPF, let it tell other people how to get there, right? So the worst thing that you can do in an OSPF network is have static routes where they don't belong. 99% of our problems is because we temporarily added a static route because something was broken and we needed to get connectivity and we forget to turn it back on again. Second important rule is filter all of your static routes that are not within your network. So if I have, for example, a gateway address where I have a way of connecting to the outside world, make sure that you filter that static address, right? So you'll add a default gateway address or sometimes a specific static address to get to your ISP. That applies only to you. Don't tell other people that you can get there. Now, in RouterOS 7, we actually found a better way of dealing with that. But in RouterOS 6, on every router that has a WAN connection, you have to explicitly filter out that OSPF or that default gateway, otherwise bad things happen. And then the third rule is the enabling rule. When should you enable OSPF on a router? Well, if you can add a router to the network by adding one static route on one router, that's okay. If you need to add 2 or more static routes in order to make this router part of the network, that router should be running OSPF and it should be telling everybody else, right? So that's sort of the enabling rule, right? The first 2 is don't do that. The last one is do that. So just a quick little bit of terminology before we take the break. So if you read the OSPF documentation, the network is called an autonomous system, right? It's basically a bunch of things that know about each other. So for example, the entire RMHAM network is called an autonomous system. The protocol that the routers use to talk to each other is called the hello protocol. It basically says, hi, this is what I know. Who are you? Let's have a meet and greet and exchange routes. And then the actual exchange of the routes is referred to as flooding. It's basically a big transfer that says, here's everything I know, big dump, take all of those. In the OSPF documentation, they all often talk about gateways. A gateway and a router is basically the same thing. A border router is a router that connects to other things. So it's basically the edge of your autonomous system. And on some links, you can actually have multiple routers. One of them has to be in charge, and that's called the designated router. So instead of sending traffic to everybody, the designated router does the heavy lifting. And then there's also a backup designated router, which is like the standby. If the primary goes down, it takes over. And then the connection between two routers is called a link. What we use is basically one of 2 kinds. Our preferred option is point-to-point, right? The 2 routers are the only 2 intelligent things on that network, and they talk to each other. If you have only one other device to talk to, it's very quick to find out when something goes wrong on the other side, right? So we use point-to-point because it makes failover faster, typically on the order of about 3 seconds or so. If you have multiple routers that share a subnet, such as if you have a point-to-multipoint network, then you have to use the broadcast terminology, where basically there's an election, one becomes the designated router, one becomes the backup router, and then you have additional routers. It works perfectly fine, but it's slower to recognize failures, and it could take 30 to 60 seconds before it actually realizes that things are down. In order to make OSPF work, every router has to have a unique ID. That router ID is used to identify how to get to the things that you want to get to. It is super important that that interface that is associated with that router ID, which is just an IP address, will never go down. Because if that interface goes down, OSPF stops working. It no longer has an address. So what we typically use is we tie it to the bridge, because the bridge can actually never go down.
Can you explain how it would go down?
Well, OSPF basically, the instance just stops working. It basically.
No. What I'm saying is, if I use this on Ethernet 1, why would that go down?
Oh, so if I unplug the cable or a rat chews through it, that interface drops, and the IP address that is associated with that interface also goes away, right? So your OSPF stops working. Yes. And so the important thing is that you tie it to something that doesn't work. You'll see a lot of the examples actually uses what's called a loopback interface. It's just a virtual interface that doesn't do anything. To tie it to that, we typically use the bridge, because the bridge, it's pretty draconian failures that takes the bridge down. And you would set that on the OSPF network. The other thing that we need to set is what's called the OSPF areas. So the areas are basically what are the networks that we are going to be routing between, right? So for RMHAM, that's the 10 dot network, the 192.168 network, and so forth. So basically, we throw all of that into what's called the backbone area, and those are the networks that are associated with it. The last thing that I'll mention here before the break is between RouterOS 6 and RouterOS 7, they completely rewrote the network interface or the routing engine. And as a result, the routing interfaces in RouterOS 7 look very, very different for OSPF than it does in RouterOS 6. It is actually an improvement, but it has a few very significant hurdles that you need to overcome that I'll talk about if we have time at the end of the talk. Basically, what I'm going to show you here is just how to do this in RouterOS 6. RouterOS 7, I've got some notes on how to do it if we get to it. But basically, the major difference is that in RouterOS 6, interfaces are automatically chosen and they automatically come up. In RouterOS 7, you actually have to specifically enable a template for every interface that you want OSPF to work over.
Why would I need to know the difference?
Depends on which one you're using.
Well, the most important thing is new devices are coming out with RouterOS 7, and you can't fall back.
Correct.
Old devices like we have in the network are all going to be RouterOS 6.
Right, and we're sort of we have a few devices that run RouterOS 7. The earlier releases of RouterOS 7 was definitely not ready for prime time. It was like a public pre-alpha that was called a beta. It's a lot better now, so you're probably okay using RouterOS 7 now. But we'll deal about the differences at the end of the talk. So. Our backbone. So in essence, the majority of the devices that you see there are backbone devices. They all use OSPF to talk to the different devices. So each of the links basically have a weight of 10, which is actually the default weight. And then for VPN routes, we typically set a route weight of several thousand. And as you have multiple VPN failovers, you should actually use route weights that are different so that you can also detect which one you want to do by preference. So for example, if the orange and blue cables were actually VPNs, I would typically set one to, let's say, 5,000 and one to 5,500. 5,000 would be the one that would be preferred. 5,500 would be the failover. But traffic would never be routed via me because I have a very expensive route, so that would never be the one. Now, we continue to use a few static routes. So if there's a device that has only one way in and out, then we would often use a static route to just say, hey, if you want to talk to that guy, send it to me because I'm the only way that you can talk to that router. However, more and more, we actually, whenever we have an outlying device, let's say Akron, for example, we will actually set up two VPNs. One to, let's say, Thoroton, which is the preferred route, and then a failover to El Magre, so that if, for example, the WAN at Thoroton would go down, then it will fail over to El Magre. Of course, if the WAN at Akron goes down, you're dead in the water, right? Because you can't talk to the rest of the world, unless you actually have two independent ISPs. So let's actually walk through how you would go about configuring OSPF. So in Winbox, the important things to set is, first of all, the router ID. The instance actually has a name. Typically, we only run one instance, so default is a good name there. You would typically set the router ID to be the bridge address. So in this case, I picked 103051, so this obviously is Devil's Head as the router. Redistribute default routes should always be set to never, right? Don't tell everybody else how to get out, because this default gateway should apply to you. It shouldn't apply to everybody else. But then redistribute connected and redistribute static routes should always be set as type 1. The difference between type 1 and type 2 has to do with how the weights are set. It's not important. Type 1 is the default to use. And basically what that says is if you have a static route that explains to you how to get to somebody else, tell everybody else about that so that they can send traffic to you and you can then forward it, right? Again, see the first law of OSPF. Only use that if you actually have no other way of getting to that route. The second one is distributed or connected routes, right? The connected routes are the ones that are automatically generated. Because you've set a route for your bridge, this will automatically add a route for the bridge as well. It will also tell other devices what all of the interfaces are that you actually connect to other devices to, so that you can talk to the devices on those links. The second thing that you need to tell OSPF is what networks do you want to route. Now, in OSPF 7, this step actually happens automatically when you set up the templates. But in OSPF 6, you would still set what the networks are that you want to route. So in the case of RMHAM, the 10 dot, the 172.16, and the 192.198 routes is what you would then add to that. And then for the areas, you can just leave that blank. Basically, since we have only one area, everybody is in the same autonomous system. Just using that default area is fine. You don't have to add something in addition, and that's automatically configured. You don't actually have to add that. Step 7 actually isn't even, step 3 isn't even actually needed, right? It will just automatically bring up all of those interfaces for you already. But it's something that you should look at and look at what all of the connections are that it has, check the costs on all of those, and make sure that it says that the neighbor is reachable, right? So it'll say the state is connected or backup or designated router, depending on what kind of interface you have. So this is actually not something you have to do. You just have to go and check that actually came up.
What's one of the things you have to check there? The network type.
Oh, yes. So the default for an Ethernet connection will come up as broadcast. If you want to make it point-to-point, you actually have to explicitly change that to point-to-point on both ends.
It'll catch you if you try to get your OSPF to come up, and one side is point-to-point and the other side is broadcast. It won't work. You got to make a match. If you have a VPN that you have to set up, it's important to also set up your default route so that you know how you get out from the device. This is true even if you have no other way of connecting to the rest of the world. So for example, here, SQA doesn't have a connection to the outside world. The only connections is through the two links to Saddleback and to Devil's Head. You still have to tell it, okay, if you don't know what to do with this, where are you going to send that packet, right? OSPF does not do a default route, right? Or at least the way we do OSPF does not distribute a default route. So you have to say, okay, by default, I'm going to send all of my traffic to Saddleback because that's one up from Thornton and that has a good connection to the outside world. So you still have to set that one static route on all of your devices. And then if you actually have a physical connection, then it's important that you actually filter it out explicitly. The reason why this is so important is, let's say I run a VPN out of that particular interface. So if I'm on Thornton, for example, there's a lot of endpoints that reach that VPN. If you forget to filter out that
WAN port on Thoradin, all of the routers that connect to Thoradin via the WAN that comes in on that interface will bring up the VPN and then say, oh, wait a second, there's a better way to get to Thoradin. It's over the VPN to Thoradin. Make that connection, boom, there goes your VPN, right? So specifically on devices where you have VPN terminations, make sure that you filter out that particular address before you enable anything else. For your home net router, that's probably not an important step. What you'll then see is that OSPF will immediately start discovering its neighbors. So if you actually go to the neighbors list, it'll tell you there who our neighbors are, and they're all connected. It'll also show the link state advertisement, right? So basically what that says is, hey, I happen to be, let me pick one here, 10.5.1.1. Sorry, I am 10.0.11.1. I know how to get to the 10.5.1.1. It basically tells you what it knows about, right? And because OSPF, every router knows about everything else, you can see from this LSA list where that is coming from. This is a super important step in debugging your network if bad things are happening. If there's a particular subnet that is going the wrong place, go look for the troublemaker. Who is actually exporting that route in this LSA list, and then go and smack down whatever that router is and fix whatever's wrong. And then if you actually start looking at the routes in OSPF, you'll see here the list of advertisements of what the gateway is and what destination address those come from. And this is also a good place to find problematic sources of data. But if you now start looking at your routes list, you'll see that we've got a static route here that goes the default route to, in this case, Ether3 Almagre, and then we've got all of those routes that show up as DAO, right? DAO says it's dynamic, A says it's active, and the little O says, I learned that from OSPF. And you can see from that how it learned the way to reach all of those. And you'll see in this case, so this happens to be the Devil's Head router. You'll see some of the traffic goes to Almagre, some of it goes to Badger, some of it goes to West Creek, some of it goes to Squaw. That route is selected based on which one is the shortest route. So moving on to lab 4, I want to now add OSPF to this router. Now, if I already have failover, why am I going to the trouble of running OSPF? Doesn't everything already work? Look at this line right here. See all the red axes? This device over here cannot talk to demo. Why can it not talk to demo, but demo can talk to it? There's no route back, but why does it work the other way?
Destination NAT.
Because we're doing natting, right? We're masquerading that interface. And so whenever packets exit this router, they get rewritten into that Buckhorn local address. So in order to make this part of OSPF, what I'm going to have to do is, first of all, undo the damage that I've already done, right? So the first thing I need to do here is go to my firewall and remove, well, I'll just turn it off, the destination NAT. Notice that now everything went to hell right? I can no longer route either in or out. What I next need to do is to enable OSPF. So how am I going to enable OSPF? I'm going to go over here to routing, OSPF, and this is the RouterOS 6 interface to OSPF. Notice that there are currently no OSPF interfaces. There is an instance, but it's not running. So typically what I do first is I go to this instance and I say, I now need to fill in the things that I need to fill in. Well, the first thing is always the router ID. It'll actually choose a default router ID, but being that I'm type A, I'm going to specify the router ID, right? So the type A router ID is 10.30.80.1. How did I choose that? It's my bridge address. Does it have to be the bridge address? Number one needs to be unique, and whatever interface I tie it to should never go down. So the bridge is a good choice. But the default route I will never distribute. I am going to redistribute connected routes as type 1. How about static routes? Do I have any static routes?
Technically, you will, because it's whatever's attached.
Well, if I add a static route, if I follow the 3 rules or 3 laws of OSPF, they're not rules, they're laws. If I have a static route, it's there for a reason. Right, other routers need to know about it, so I should add it. So by default, I would just always enable that. And the filters, since I don't actually have a WAN connection, I'm directly connected to the net. I'm not going to mess with the filters, but that's where I would set the default filters. So I'm going to turn that on. Still not running. Why is it not running? Well, I haven't defined networks yet. I need to define networks. So the networks that I'm going to define is 10.0.0.0/8. Sorry, it's 8, right? That's basically all the 10 dot networks. Is there anything other than a 10 dot network over here? What? Where? Yeah, not here, right? In the RMHAM network there are. These are all only 10 dot addresses, so I'll get away with only doing 10 dot. As soon as I define that network, notice that my instance now says running, right? So OSPF actually has something to do, so it's running. And if I look at the interfaces,
Note that your ping started too.
both of my interfaces are up. They discovered the networks, and in our case, we're the backup router. Not only did my ping started routing here, but look right there.
OSPF is pretty much magic.
The router now discovered us. And if I now go to look at my routes, notice that suddenly I know how to get to everything on the RMHAM network, and everything on the RMHAM network knows to get how to get to me. What would happen if I pull either one of the orange or the blue cables?
It'll go the other way.
Well, let's look at the routes. Notice that the routes are either WAN 1 or WAN 2, right? Can you pull the blue wire?
Wait for it.
Notice that they now all of a sudden discover WAN 1. This is actually a fairly expensive operation, right? Because basically what everybody learned when the blue wire is plugged in is that you're down here in the southern part of the network. You just send the traffic up to Lee Hill will get it to demo. If you're up in the northern part of the network, you send it to Buckhorn. Buckhorn will get it there. If the blue wire gets pulled, there's only one way to get there. All of these guys down here now need to learn, oh, wait a second, I now need to go to Buckhorn. That's the only way that I can get there. Or vice versa, all of the guys in the north would need to learn how to get to Lee Hill. However, notice how fast that was, right? It took literally seconds for all of that information to propagate to all of those other routers. In the real world, where the ping times between the routers are not, 2 or 3 milliseconds, it takes a little bit longer, but not a whole lot longer, right? It's typically within somewhere between 10 and 30 seconds, the entire network has relearned all of the routes.
Denver to Grand Junction right now is about 15 milliseconds average. And you look at a failover there costing maybe 5 to 8 seconds. That's a lot better than a couple of days to try to get all the routes back if you took a lightning strike and were doing it manually.
So what I didn't have to do in this case, or I should have done, but I didn't, was to actually change the weights, right? So notice that right now, it's 10 milliseconds from Buckhorn to me, and another 10 milliseconds from me to Lee Hill. That actually means that I'm probably going to carry the bulk of the Buckhorn to Lee Hill traffic, because the other way to do it is to go to Horsetooth, then to go to Firestone, and then come back, right? That's 4 hops instead of just 2 hops, right? So if I want to properly route this, what I need to do is to go and change the weights. What does it take to change the weights? Well, it depends on whether you have a static interface or a dynamic interface. If I have a static interface, such as what is shown here, come on, give me the thing. What happened to WAN 2? Did I unplug it?
Yeah, you told me to unplug it. I can plug it back in.
Duh. Sorry, I got tricked.
It'll come back.
We were seeing if you're awake.
There it is.
That's not very indicative of whether you're going to get an intelligent answer. Notice that these have a D in front of them, right? That means they're dynamically assigned.
And notice that it disappeared when it was unplugged, hence dynamic.
So if I click on this, notice that I can't change the weight, right? Or it's called the cost here.
Grayed out.
How do I change that? Well, what I need to do is I need to copy it and then say, oh, I want to make this weight, let's say 20. And then if I hit OK, it'll go away, it'll apply. Now notice that it basically dropped the one automatically and replaced it with something else. So this will no longer go away whenever the link drops. Am I done? Chris is exactly right.
Got to do both sides of the link.
If I now say from here, it's 20 to Buckhorn, but Buckhorn thinks it's 10 back to me, I'm going to end up with split routes, right? My outbound packets goes one way, my inbound packets come another way, right? So it's always important to make sure that you set those on both ends. And also, while I'm at it,
Yes.
notice that this says broadcast, right? If I set the weight back to 10, so everything is fine, but I make this point to point, notice my,
The neighbor should go to 0.
that is probably sent to all. The other side was smart enough to actually change to point, but normally what this would do is if I had not plugged into the WAN, the bridge, it would actually say the other side is down, right? Because I set it to point on the one side, and the other side is probably set to broadcast. So it would fail. In this case, it actually discovered that network. Oh, actually, that may not be true. Let me just see. Where's my neighbor list?
To your right, there you go.
Neighbors. Oh, no, it did remember it. So I should have chosen a better example. But the long and the short of it is, it's important that you keep those definitions
They need to match.
consistent. Otherwise, bad things will happen. So I'll just sit this back.
When
to
you least
broadcast.
expect it, it will break itself.
So the long and the short of it is, in our little setup here, I had to do two things, right? I had to fire up the instance and set the networks, and everything just worked, right? That's how OSPF typically needs to work. If you're the type A, we typically we want to set the weights, and we want to set a whole bunch of other things because we want to actually steer our traffic, right? We want to have a preferred path that we should use all of the time, and then fail over to something else, or have the secondary traffic going to where you want to go it. Right, all of those steps that I showed later in the slide, steps 3, 4, 5, 6, and so forth, those are all how you can have greater control over OSPF, and then make it do the right thing to send the traffic where you want it to send. So, not quite the greatest thing since sliced bread, but pretty darn close. So how do you debug OSPF? Well, there is in the logging that you can actually enable. You pick the topic OSPF. Do not set it to raw, because you will get so much information. You will have no idea what's going to happen. So anything but raw, it should show. And it'll basically tell you when it's the neighbor goes from down to connecting to full, and has the interface. Sometimes on Mikrotik, you get this weird error message that says database out of date. That basically means that somebody is sending you a set of entries of routes that it knows about, but it had sent you a newer set of data before, and now it's sending you older data, right? What the heck? There's only one way to fix it. Reboot the router. Something weird went wrong. I haven't seen that in a long time, but in about 7 or 8 iterations of RouterOS ago, that was a sort of a problem. But then look at your logs and just see in the logs, it'll actually tell you as things connect or disconnect, and discovering the neighbors, it'll actually tell you what's going on. If we use this so that it logs to a central location on Thoradin, and we can see all of the errors in that one location. If you click over there on the AS border routers, that tells you what is at the edge of your network, right? It basically tells you what are things that are connecting to the outside world. In our case, we don't actually do something with that, but if we, for example, reorganized our network to, let's say, Colorado being one autonomous system, New Mexico being one autonomous system, then the border between those two will be a much more important device, and this is the place where you would see it. So far, even with 240 sites, we've not run into any issues with OSPF scaling properly. The other thing to watch out for is things like this. So notice that in this case, this particular network is reachable by Ether1 and by Ether2 with the same distance. When that happens is typically in a situation such as you have a loop. In this case here, we can go from Devil's Head to Badger to Cripple Creek back to El Magre. And so if you're on something that's attached to both Devil's Head and El Magre, very often there are equal weights to reach one of these other routers in the loop. So if you have something like that, many times it's not a big problem, but you can just tweak one of the weights, right? So instead of the weight between Devil's Head and Badger being 10, you make it 11, right? Then you break that tie, then one side or the other becomes the default preferred route. As far as VPNs are concerned, as I showed you in the connection, if a VPN comes up as a dynamic interface and you try to set the weights to it, the weights actually won't take, right? Well, here the problem is that it's not a problem that the OSPF interface is dynamic. It's the actual interface itself in the interfaces list that's dynamic. And in that case, it's a two-step procedure. So you first have to go to the interface list and make a copy of it there and make that connection permanent. So let's say I have an OVPN connection to Thoradin. I would go to the interface list and make the OVPN Thoradin interface a permanent connection rather than a dynamic connection. And then I can go to OSPF and in OSPF say, okay, now this particular permanent connection will have the following properties. If you don't do it that way, then every time that VPN drops and come back up again, it'll recreate the interface in OSPF and it'll have whatever the defaults are. Now, there is a way that you can go in the defaults, in the interface list, you can have an interface that says all, which sets a default value. But there's a much better solution in RouterOS 7, which is to actually set up that template for the interface, and that solves the problem. Steve?
No, I'm just holding the camera.
Oh, okay. I thought you were trying to ask a question.
I'm following you around.
Oh.
At least it's not Doug and his wandering,
So
or Mike.
in the interest of time, I would simply skip ahead and talk a little bit about RouterOS 7. So as I said, RouterOS 7 is a significant improvement over RouterOS 6, but it was a complete rewrite. And as a result, not only did the interface changes, but what happens under the hood is completely new. This is great if it works. So in some of the earlier iterations of RouterOS 7, things were very unstable, but it's really settled down. You know, as an indication, in the early days of RouterOS 7, we would get an update like every second day. That's now slowed down to about once a month. So things are starting to settle down, and our experience with using RouterOS 7 in a few places, it actually has given us capabilities that we did not have before. So we will probably next year start to gradually upgrade our entire network to RouterOS 7. Right now, it's mostly 6 with just a few 7. On that NetLab, I've got about half a dozen running on 7, half a dozen running on 6. 6 and 7 talks to each other. There's no problems about that. The main thing is that the interface is a little bit different. If you have a new device that runs only RouterOS 7, then just use RouterOS 7. It's perfectly fine.
If you're going to upgrade something in the field, I would highly recommend being there.
DFIU originated from the fact that people did remote upgrades, and then you get a phone call that says, hi, I broke something. Can you go fix it? Doesn't make you very popular.
Willem,
Yes.
there's a question from, I can't do both. There's a question from the chat from Greg, K0MGL. Is RouterOS 7 okay for a new design or implementation?
Sure.
Implementation
Definitely.
such as an initial
Yes.
router?
Yes. Yes, I think it's ready for that. So the huge jump forward in OSPF 7 is that the routing filters are now authoritative. So one of the problems we had in RouterOS 6 is that if you have a network such as 10.0.0.0/8, and you put in a filter that says, hey, I'm doing this funky thing because my ISP is also using the 10.network. So don't export the fact that there's a route on my local router that's 10.11.20.32. That is how I connect to my ISP. You would put that filter in the OSPF out filters, and RouterOS would say, well, but you told me that I should distribute all the 10.networks, so I'm going to still distribute that, right? And this created all kinds of problems, LARC being one of them, where we had a local net that we had to use that's within our address space, and we had no way of filtering that route at the source. You could filter it at the destination, but you basically had to go to every other router on the network and say, just ignore what LARC is telling you. They don't know what the hell they're talking about. In RouterOS 7, that is no longer the case. So the big change in RouterOS 7 is that those filters are authoritative. What I don't like about RouterOS 7 is that the rules are completely free format. This is great if you know what you're doing. If you're learning this, it's a nightmare because the error message is typically syntax error. It's like the old Carnegie and Ritchie C compiler. It just says something's wrong. It doesn't even tell you exactly where. So in this case, this is the rule that we apply. And the nice thing about this is we have one rule to rule them all, right? We have one rule that we applied for both exporting rules and importing rules. And instead of saying what we don't want, we say what we want. So this rule reads, if the destination is 10.00.8, or the destination is 172.16.00.16, or it's 192.168.00.16, and not 192.168.00.22, accept. Otherwise, reject.
What's the reason behind 192.168.00/22?
Well, first of all, what's covered by 192.168.00/22?
0, 1, 2, and 3?
Right? It's the lowest four numbers in the 192.168 address space. Why would we not want to distribute those? It's most often somebody's home router or Comcast or CenturyLink or something like that uses those. Now, they'll also use 10. Sometimes, but the 192 is much more common. So what this basically says is the RMHAM space starts with 192.168.4 and goes through 192.168.255. Only those are the ones that we're going to deal with. However, when we say do the networks, we say, hey, just do all of the 192.168. The filter will take care of getting rid of those.
We're no longer using that.
You should blow away that configuration before you connect to the network.
So one of our
yes, you're
members
right.
actually used the default configuration, and 88 was in use until last fall. We got them to move.
So this rule, sorry, go ahead, Mike.
Can you quickly explain what the chain is in that filter rule box and where to either configure or create that?
So notice that I called this chain OSPF RMHAM, right? You can actually have multiple rules, and as long as they have this, they're in the same chain, they will all be executed one after the other. In this case, since we have only one rule, the entire chain consists of only that one rule. If, for example, we use this generic rule, but you're on a network that also requires you to do 10. You can add a rule before this one that says, if I'm this other special case, reject it. Then you add this rule that says, and everything else, so this is definitive. It's either going to accept or reject. If you only say reject this other one, but you don't say accept, then it will only reject that rule, right? So these rules in 7 is almost like a little programming language that until you either reach the accept or reject decision, it'll keep on doing the next rule, right? So it's a little bit more flexible, but a little bit beyond this class.
Something that tells you what the context of the message is. In other words, how to set that up. In other words, you got to have you got to have a library to decide that.
No, that's the problem, right? In the older configuration, there was actually, drop downs and selectors and stuff like that, right? It made it fairly easy. In RouterOS 7, because it's like a programming language, you have to go and read the documentation to try and to figure this out. And for the longest time, the documentation and the actual implementation did not agree. So it took us a while to beat our heads against the wall. The documentation is starting to catch up, but it's still not perfect. Thank you.
Their development lags behind their documentation by years.
Well, at least months. So in this case, what I do is just, this rule works for anything RMHAM. Just use it, and if there's an exception, call Joey. So then to configure the actual RouterOS, OSPF instance in RouterOS 7, notice that this looks very different than it did before. So we have a name. That name is actually different depending on whether you've upgraded the router or you're creating a brand new router, but the name is sort of irrelevant. Then, because I'm dealing with OSPF, there's actually an OSPF version that's called OSPF 3 that also deals with IPv6, right? Since we're only doing IPv4, we stick to OSPF 2, it's simpler to deal with. VRF stands for the vertical routing filters. So that's just the core routing rules. So in that case, we just leave that on main. And then we set the router ID here. In this case, 192.168.12.1 was my test router that I was using. So this should be your breach address. Same rules apply. From here on down, things look very different. So first of all, the redistribute is now 6 gazillion options instead of the 3 that we have before. So it says, do you want to redistribute connected routes? Do you want to redistribute static routes? Do you want to redistribute RIP? RIP is like an older version of, or a protocol that became before OSPF. We don't use it anymore. What about OSPF? Well, you probably want to turn on OSPF, right? So you tell others about your OSPF routes. Do you want to do BGP? Do you want to do the VPNs that are connected to you? What about fantasy? Well, I'm more of a science fiction guy, so I'm going to not leave that.
What does that mean?
I don't remember. What about modems that are directly connected, right? So some devices will actually take like an LTE modem, right? Do you want to distribute that? So you have a lot of options of what you can turn on. Typically what we do is just the standard ones, connected and static. OSPF sort of learns about OSPF itself. And then the other thing is for both the in and out filters, I'm going to set this to OSPF RMHAM because it's that rule that I'm using that works for both imports and outports. I can, of course, customize that to different things if I really wanted to, but this is typically how I set it up. And then the totally new thing is the interface template. So the interface template takes the place of setting the network and the area that I had to do before. So in this case, I've selected the interface Ether1 to Thoradin. The area is backbone, which is one of the defaults that shows up. The network type is point-to-point. So when I create this interface, I typically select point-to-point unless it's a broadcast address that I need to have. All of the rest of the stuff here you can leave empty except for the cost. The cost you need to explicitly set as to the kind of device that you have. Typically it's 10 if it's a microwave link. If it's a VPN link, it will be 500 or 5,000 or whatever the value is. And here's another example. This case is a virtual private network. So it looks exactly like the physical interface. It's set to point and so forth. But notice that the interface is now that VPN interface. And make sure that you get the static one. And notice that I set the cost to 5,000. Here's what's new in RouterOS 7. On Thornton, for example, we have lots of VPN connections that come in. For each of those that is an OSPF connection, we have to go and set manually the weight on each of those, which is a pain because, every new connection, you have to set it on both sides. In OSPF 7, there's a new trick. If you leave the interface blank, but you set the network to the network that will be used by the VPNs, all of the VPNs that connect to that network will get that particular setting.
They'll automatically inherit those.
It'll inherit it from this generic network setting, right? So that you could, as long as all of them share, let's say that 5,000 weight or whatever the big weight is that you set, you only have to set that once, set the type, set the weight, and so forth, and all of those interfaces will then inherit that one value, right? Huge win when you've got a complicated site like Thornton.
I think there's about 170 VPNs on Thornton. You can imagine how difficult that gets to try to touch 170 endpoints.
Right. Now, where this gets ugly is what if I now have a connection that goes to somebody that needs to have a different weight? Well, for that, I would go and select a specific interface and make something that's specific to that particular interface, right? But so this is a big win in RouterOS 7. So basically, in terms of the templates, the key thing is that when you fire up OSPF, unlike in RouterOS 6, those interfaces don't just automatically populate. You have to manually go and add an interface template for each device or each interface over which you want to exchange OSPF. So what you need to do is, as I showed in the previous ones, either do it on an interface by interface basis or do it for sort of a category of interfaces by just setting the network addresses for those. The network type needs to be explicitly set. So because in the interface template, you have to go and set that template before everything happens, there's fewer chances of things getting set by default and getting set to the wrong one, right? So whenever you go across an Ethernet network, it, in RouterOS 6, always defaults to broadcast. Well, when we have microwave links, we typically want those to be point-to-point. So we have to explicitly go and change the broadcast to point-to-point, and you do it on the one side, and then you go and do it on the other side, except the other side is now on the other side of the link, and you just drop that link because you just changed this side of it, and now you have to go and undo everything so that it will reroute so you can get to the... There's lots of ways to screw this up. It's just a little bit of a more straightforward that explicitly you have to say what you want, you set those things, specifically the network type and the weight, and then it will come up and we'll have the regular settings there. The other thing that's new in RouterOS 6 is that you'll notice that there's this flag called priority. When you upgrade from RouterOS 6, the priority for everything is set to 1. The way that priority works is the higher the priority, the more probable that that router will be elected as the designated router. If you're on a point-to-point link, doesn't matter. There is no designated router, right? It's two routers that talk to each other, so it actually has no effect. However, in a broadcast network, by setting the priorities of the different routers, you can select which one you want to be the designated router, right? So as a general rule, the way we configure our network is that we choose the side that is closest to authority, typically to be the .1 router ID, and we'll prefer that to be the designated router, simply because it's more likely that we could reach it from the authority side than from the other side, so that's generally desirable. But sort of something that you can actually now configure in RouterOS 7 that wasn't true in RouterOS 6. So as far as actually upgrading from 6 to 7, in some of the earlier iterations of RouterOS 7, I have actually had to go and net boot the device to get it up. So I definitely recommend that you're actually on site when you actually upgrade something, rather than call John or somebody and say, oops.
And have a PC with you and an Ethernet cable.
In this case, something that I didn't talk about, but RMHAM is your friend, right? RMHAM is this protocol that is proprietary to Mikrotik, that as long as you can, at layer 2, right? So at the Ethernet level, talk to the device on the other side, you can get into the GUI. And so RMHAM has saved our butts many, many times when you mess something up. But generally, I recommend that you're on site when you touch anything important. One important thing that happens when you upgrade from RouterOS 6 to 7 is that all of your VPN OSPF connections go away. So all of your OSPF connections that are attached to an actual Ethernet network will get upgraded from 6 to 7, and OSPF will keep on using those, automatically create templates for them in RouterOS, in the RouterOS 7 config. It does not do that, at least as of RouterOS 10.10 was the last one I tried. 7.10, it did not do that. Now, they've been working on their upgrade software, so it may change in the future. But generally, if the way that you connect to a device is by a VPN, and that VPN runs OSPF to reach it, you'll probably lose connectivity to it. So again, the VPN itself will go up, but OSPF will not, so you will have to probably ROM on into it to actually do it. The second thing is that when you upgrade, the interface templates will be over-specified. So in this interface definition, it will both say both the interface as well as the network. And that network will be whatever the IP address on that interface is. My preference is to just tell it the physical interface name rather than the network. Because if the network changes, then obviously this connection is going to be different. You may actually argue that there's a better way to do that, which is here, instead of setting the interface, you set the network, right? So if, for example, I know that the connection from Saddleback to Squaw is the 10.20.13 subnet, if I plug that particular Ethernet cable into the wrong port, that connection is not going to come back up again, right? Whereas if you actually do it based on the network definition here, it will work regardless of what port you plug it into. However, that's going to confuse the hell out of me because Ether1 Badger is not running, but I can talk to Badger. How is that happening, right? It's a bit of a, not quite policy, but it's a way of doing things that causes the least confusion. So I still prefer to actually specify, the actual interface name rather than the subnet. The other thing that breaks between RouterOS 6 and 7 is recursive routes. So remember we talked about the recursive failover where you're actually connecting to 11, 1.1.1.1. The way that that works in RouterOS 6 and 7 is sufficiently different that that will stop working when you do the upgrade. So go and look at the resource that I'll show you on the next page how to fix that. You just need to change the target scope on one of those and it'll be different. The other thing that, of course, is different is the routing filters, right? The way that the routing filters work in RouterOS 7 is completely different. Well, how I learned how to do routing filters in RouterOS 7 is to implement them in 6 and upgrade and see what they looked like, because the documentation was not very helpful. But it will actually do that correctly. So, so far, I've not found any instance where the routing filter actually didn't work. However, because we have this new, much better routing filter that selects what we want instead of what we reject, typically my procedure is once I've upgraded it, I create that new routing filter and then delete the old ones and use the new one instead. So I have 10 more minutes. I've got a lot of interesting things I want to show you there, but I think you're all probably too tired to read anything anymore. The one thing that's sort of interesting is I can break that route in an interesting way where I actually do failover routing on my microwave links. What that basically amounts to is that if I were to fail the access point, I can no longer talk to the client side because the default gateway for that device is actually on the remote end. And by setting a failover route on that second device, I can actually fix that. I'm going to take 2 minutes to actually just show you how to do that. So what I'm going to do here is to connect to 10.20.17.4. If I can type it. This is just a trick I want you to learn. So notice that I have a static route and a second static route that I have commented out. What this does is it has 2 default routes, one with a distance 1, one with a distance 2, that points to 10.20.17.1, and another to 10.20.17.2. So this is the final exam for this class. If I were to pull the power on this access point right here, and I connect directly by Wi-Fi to AC0KQ, can I talk to this device from my laptop? The answer, of course, is no, right? Otherwise, it wouldn't be an exam question. So let me just do that real fast. So unplug here. Stop. Come on. So I'm running a CPing here that I can talk to the LHG, but I can't talk to the QRT and I can't talk to the switch. Now look at the connections. I am connected directly to this router here. This red wire runs through that switch and to this device. I can talk to this device, but I can't talk to the one that's in between them. Why is that? Explain. I will show your work.
Well, I would, but I couldn't.
So on this device, if I reconnect to it, notice that the static address that is active is the second one, 10.20.17.2. What that means is that the answers back goes to 10.20.17.2, this device. What about that guy? Well, its default gateway doesn't have that failover route. It sends everything to Saddleback, but it can't get to Saddleback because I just unpowered it. But why do I need to? Right? My laptop is connected directly to this via Wi-Fi, and there's this red wire that goes directly to it. Why can my laptop not talk to that device? My laptop is on the 10.30 network. That device is on the 10.20 network. Even though we share a common device, we are on different subnets on this device. And so that device needs to send a packet to the right router that knows how to get to that other subnet. So, Emmett, you passed the final, the rest of you all failed.
You get lucky once in a while.
So, if you want to learn more, call John. Here are some resources. So the Mikrotik wiki is actually pretty good. On my website, I've got specific discussions of how to do failover, specifically recursive failover on RouterOS 6, and also then a discussion of RouterOS 7 and how to upgrade to RouterOS 7 and all of those things. If you're interested in these slides, they're all on the RMHAM website. So if you go to rmham.org, RMHAM University, under the past syllabuses, all of these slides will be there, so you have access to it. And of course, John's phone number. Oh, it's on the door. So thank you for attending. I appreciate
Willem,
you suffering.
Before we go, there's a couple questions from the chat.
Okay.
Aaron A0QQ asks, where are VPNs used within the RMHAM network?
So all of the red wires there are VPNs, right? So we typically use that as either a backdoor or a second way to get into devices, right? So for example, we have a VPN over to Grand Junction. So if we can't get to any of the devices across the continental divide, we always have another way to get back into it. So we typically don't use those for passing any active traffic, except for a few outlying locations like Akron, for example. We don't have microwave into Akron. So there are a few sites that that's still our only way in is through commercial internet.
Akron will probably be fixed this summer. Burlington may never get fixed. Durango, we're hoping sometime in the next few years.
So we try to use that only as backups, except in a few exception cases like that.
Second question. Speaking of the RouterOS upgrades, between 7.12 and 7.13, they split out the wireless package to separate out the Wi-Fi drivers. That's a major change, so I would recommend being nearby. Although he has personally upgraded 12 units and they all work correctly.
That has been my experience with RouterOS upgrades recently. They've become a lot more stable. But, pause for paranoia. A lot of these sites is a long drive. If you have it on your desk, well, bring a hammer. Right. Or at least have eyes and a pair of smart hands that can take a hammer to the device if it's misbehaving. Any other? What? Yes, so safe mode is something that if you make changes to it and it loses connectivity, it'll actually revert back after whatever time period you set.
Yeah, that does not work on upgrades.
That doesn't work for upgrades. And we've had, even within RouterOS 6, once in a while, the device just doesn't come back after a firmware upgrade, bad NAND or whatever. Just don't do that to remote sites, or at least not important ones. So with that, thank you very much. Please, our next activity is NerdFest, which is in this room on February 10th. Thank you. It's people like Chris Keller that's going to give us a talk about what again?
Small satellite antenna rotators.
Right.
Small satellite antenna rotators.
And Dave is going to talk about surface mount devices. I'm going to talk about the new latest and greatest thing in network monitoring called CalmOn, which is a way that you can monitor all Starlink devices. Glenn is going to talk about EOSS and balloon uses. Except for me, a lot of really smart people talking about very nerdy topics. So you will all love it. So thank you again, and we'll see you at NerdFest, and in the next week after that at the ARA Swap Fest. So thank you very much. We'll see you soon.
It's not ARA anymore.
It is the Rocky Mountain